Yes. You can be.
Okay.
Good morning, everybody. Can you hear me? How many are there?
22.
John, muted.
Unmuted.
Can you hear me?
Yes, sir.
Okay. Good morning and welcome back. So last time we were discussing these controllability tests. We have already discussed one part of the theorem. The second part of the theorem will be proving today. So what did we prove last time? Anybody?
So we were discussing linear dependence or independence of vector functions.
That was, the immediate last lecture. What did we discuss? We actually proved the first part of the theorem for testing the controllability of a system. We actually proved that for a system to be controllable, the necessary and sufficient condition is that the controllability grammar must be non-singular, isn't it? Yes, do you remember?
Yes, sir.
Now the second part of the theorem needs to be proved, and this is very important because this theorem will actually lead us to the most popular controllability test, which is actually used for testing whether the system is controllable or not. So what is the statement of the theorem? The second part of the theorem. The second part of the theorem says that for a system to be controllable, the controllability matrix must be a full rank matrix. And how do we define the controllability matrix? Let me first of all put the theorem. So the second part of the theorem was, first part हमने प्रूव किया, पार्ट 2 क्या था इसका? The necessary and sufficient condition for the system given by equation 1. What is equation 1? Equation 1 is x dot equal to ax plus bu, where x0 is defined as x0. So the necessary and sufficient condition for the system given by equation 1, this is our equation 1 basically, to be controllable is that the controllability matrix defined as UC is equal to B AB A square B for up to 8 to the power n minus 1B is a full rank matrix. That is, it has a rank equal to n. Okay. So the necessary and sufficient condition for the system given by equation 1, that is whose state space model is given as x dot equal to x plus bu and the initial conditions are given, to be controllable is that the controllability matrix is a full rank matrix. And how do we define the controllability matrix as? Controllability matrix is defined as UC is equal to B A square B A to the power n minus 1B. B, you know, this is this B. What's the size of this B for a single input, single output system? Size of B is? Yes. Rule number 3. What is the size of B? Rule number 3 is not online. Rule number 11. Rule number 11. Rule number 15. Rule number 21. '24. 27. So if nobody is here, then who is attending the class actually?
Sir, n cross 1.
Who is rule number 27? Yes. Who is rule number 27 and who is rule number 24? Rule number 28. Shekhawat Kumar. Are you online? Rule number 28. Roll number 37. Roll number 37. '46.
Yes, sir.
46. What's your name?
Yes, sir. Hi, Pradeep. Hello.
Can you hear me?
Yes, sir.
What's your name?
Yes, sir. Manish.
Manish, tell me what is the size of B for a single input, single output system?
Single. Sir. N cross 1.
N cross 1. So it's a single column. Rule number 5. Rule number 5. Nasir Hussain Sheikh. Rule number 7.
Yes, sir.
Okay, you are online. Rule number 8.
Yes, sir.
Rule number 9.
Present, sir.
1.
Yes,
Rule
sir.
number 1. Rule number
Yes, sir.
5.
Present.
Who is rule number 5? Rule number 10.
Yes, sir.
12.
Sir, five is present.
Sir, 12 present.
तो आप कहाँ पे थे? Rule number 5.
सर मैं यहाँ पे था सर, मेरा माइक नहीं चल रहा था.
Rule number 12.
Sir, present.
13. Rule number 19. Rule number 19.
Yes, sir. Yes, sir. So, Mike.
23. 23.
Present, sir.
28. 'Roll number 28 will not be allowed in the class from today onwards. 29.
Yes, sir. 29.
30.
Yes, sir.
31.
Yes, sir.
32.
Yes, sir.
34.
Yes, sir.
37. 37.
एक्सक्यूज मी सर.
Yes.
सर आवाज बहुत स्लो आ रही है आपकी.
Anybody else having the same problem?
No, sir.
Aryan, this is a problem with you, not with me.
सर पर मैंने पूरा वॉइस रखा है फिर भी.
38.
37 present, sir.
Yes,
37
sir.
present.
Yes, sir. 38 present.
40.
Yes, sir. Present, sir.
46. 46 is here. 46,
Yes, sir. 46, yes.
47,
Yes, sir.
52,
Yes, sir. Yes, sir.
53,
Yes, sir. Present.
54,
Yes, sir.
55,
Yes, sir.
59,
Present, sir. 59.
60,
Present, sir.
61, 61, 62,
Present, sir.
64,
Present, sir.
66,
Present, sir.
67,
Yes, sir.
69,
Yes, sir. 69.
70,
Present, sir.
71,
Present, sir.
73,
Present, sir.
74, 74, Samiksha,
Present, sir.
75,
Present, sir.
76, 76, 77,
Present, sir.
79,
सर 76 प्रेजेंट सर आवाज ही नहीं आ रही थी आपकी
अब कैसे आ रही है?
सर अभी आई पता नहीं आवाज आ नहीं रही है आपकी
79, 80,
Present, sir.
81,
Present, sir.
82,
Yes, sir.
84,
Yes, sir.
85,
Yes, sir.
86,
Present, sir.
87,
Present, sir.
91,
Yes, sir.
92,
Present, sir.
okay. Now, as I was telling you, the size of this B vector is n minus 1. And what's the size of AB? What's the size of AB? A is n cross n and B is n cross 1, isn't it? The size of AB is n cross 1. Similarly, the size of A square B is n cross 1. So this is also n cross 1. So how many n cross 1 columns are here in this matrix? N columns. The size of this matrix is n cross n. So if this matrix you see is a full rank matrix, then we say that the given system is controllable. Let's prove this. Let me give the proof of this theorem. We know that the condition for controllability is given by defined by the or is given by the following equation. That is x0 is equal to minus integral of 0 to tf e to the power minus at b ut dt. Do you remember this equation? Where from has this equation come actually? We have already discussed this equation last time, because you know basically that the solution of a state space equation is given by xt equal to e to the power minus at x naught plus integral of 0 to t e to the power a t minus tau b u tau d tau. Now at some final time tf, at some final time t equal to tf, we have xtf equal to e to the power minus a tf x naught plus integral of 0 to tf e to the power a tf minus tau b u tau b u tau beta. Isn't it? Then if I've already proved it last time. So this equation, why from this equation has actually come. Now for when we define controllability, we take the final state to be the origin. Isn't it? While defining controllability, we take the final state to be the origin. That is xtf we take equal to 0. So when we substitute it here, what do we get? We get 0 is equal to e to the power minus atf x0 plus integral of 0 to tf e to the power atf minus tau b u tau and beta. Or I can write, if I take this equation on this side, what do I get? I get minus e to the power minus atf x naught is equal to e to the power atf I can take out here, integral of 0 to tf e to the power minus a tau b u tau beta. I'm again refreshing where from this equation has come. So now if I pre-multiply on both sides by e to the power, this is e to the power, this is e to the power atf, it's not e to the power minus a. It's like this. So if I pre-multiply on both sides by e to the power atf, pre-multiplying on both sides by e to the power minus atf, what do I get? So this becomes my e to the power minus atf, e to the power atf, this becomes e to the power 0, that's I, so this becomes minus x naught equal to, this also becomes I here, so this is 0 to tf, e to the power minus a tau b u tau beta, or x0 is equal to minus integral of 0 to tf e to the power. Now I can use it, I can change the variable. Instead of tau, I can use t. You can still continue with tau, that doesn't matter. So this is e to the power atb ut dt. That's why from this equation has come. This I had already proved last time, isn't it? So this all will come in this bracket as the proof of this. Now I get back to this. Now I have x naught equal to minus integral of 0 to tf e to the power minus at b ut dt. Now we have already seen this e to the power minus at, that's the matrix exponential. Matrix exponential can be evaluated by Cayley-Hamilton theorem. And using Cayley-Hamilton theorem, how can we express a matrix exponential as? Using Cayley-Hamilton theorem, e to the power minus at can be expressed as, yes, anybody? We've already इसमें एग्जाम भी हुआ है आपका. So how can you express e to the power minus at as using Cayley-Hamilton theorem?
So beta naught plus beta 1a plus
Yes, beta naught I plus beta 1a plus beta 2a square plus so on, isn't it? I can express it as a what you call matrix polynomial. So we can express it like this: beta naught I plus beta 1a plus beta 2a square plus so on, beta n minus 1 a to the power n minus 1. Isn't it? Or I can write e to the power minus 80 in short format, summation of k is equal to 0 to n minus 1, beta k a to the power k. Is that clear? Is that okay? Now I substitute for this e to the power minus 80, I substitute this thing. So I can write, so therefore x naught can be written as minus integral of 0 to tf. Then I have e to the power minus 80 like this. So instead of e to the power minus 80, I can write summation of k is equal to 0 to n minus 1, beta k a to the power k, isn't it? And then I have b ut like this. B ut dt. Are you getting me?
Yes, sir.
Okay. Or I can write x naught is equal to, I can write it like this, minus summation k is equal to 0 to n minus 1. Beta k is a scalar, it can be just moved here and there. I can write it like this: a to the power kb integral of 0 to tf beta k ut dt. Beta k, actually you have to remember that beta k is also a function of time. Here also I will write a function. Okay. Now, if you know this ut, or if I just put the values of beta k here and then evaluate this integral, assuming that ut is known, for each beta k I have to evaluate this integral. That means for k is equal to 0, I have to evaluate this integral k equal to 1, because k varies from 0 to n minus 1. So I have to evaluate this integral. So once I evaluate this integral from k is equal to, for all k's, that is 0, 1, 2, up to n minus 1, I call this as, assume integral of 0 to tf beta kt ut dt is equal to alpha t. Because it is a proper integral, so if I evaluate it, assuming that I know ut, so I can evaluate this integral for every beta k. So let's say for beta naught I evaluate it, I get it as alpha naught. For beta 1 I evaluate it, I get it as alpha 1. Similarly, for beta k equal to n minus 1, I evaluate it as alpha k, alpha n minus 1. But this is subject to the condition that I know ut, because knowing ut actually is what actually we are going to prove. So we will actually see what will be the condition for this alpha k, under which this alpha k can be evaluated. So I assume that this is equal to alpha k and substitute it back here. So what do I get? I get x0 is equal to minus summation of k is equal to 0 to n minus 1 a k b, and instead of this I write alpha. Or I can write this as x naught equal to, if I open up this, this minus I will keep outside, and I go on expanding this summation, through the summing block. दिस ये जो टर्म है यहाँ पे मैं एक्सपेंड करता जाऊंगा. k equal to 0 पहले है. k equal to 0 पे a raised 4 0 I हो जाएगा. So what will be the first term? First term will be beta alpha naught. Sorry, b alpha naught. Then second term will be a b alpha 1. Then the next term will be a square b alpha 2 plus so on. The last term will be a to the power n minus 1 b alpha n minus 1. Is that okay? Yes, I need at least one response.
Yes, sir.
Okay. So this is x naught equal to minus this thing I can write as b. I'll write it like this: b ab a square b so on a to the power n minus 1 b. And here I will write it as alpha 1, alpha 2, so on, alpha n minus 1. Can I write it like this?
अल्फा नॉट से स्टार्ट होगा ना.
Alpha naught, so sorry. This is the alpha, starting from alpha naught. It's okay?
Yes, sir.
Now this matrix, we'll call this as UC. Okay? So I can write it as x naught equal to, this is equal to here, minus UC, then this. Let me name it as big alpha, like this, like this. Okay? Now, what will be the condition for the existence of this alpha? The condition, if I want to evaluate alpha, I have to pre-multiply this on both sides by UC inverse, isn't it? Are you getting me? Alpha
Yes,
obtain
sir.
करने के लिए alpha, what will be alpha equal to? This big alpha will be equal to minus UC inverse x naught. So this actually implies that alpha can be evaluated only if this UC is an invertible matrix. Isn't it?
Yes, sir.
Or UC has, in other words, we can say if UC has rank, if it's a full rank matrix, if it has rank equal to n, then only this alpha can be evaluated, which we had assumed here that we had actually put it equal to this alpha subject to the condition that U actually exists. Because if this U exists, then only I can calculate alpha. Now this equation actually gives me the condition for evaluating alpha. The condition for evaluating alpha is that UC must be a, that means which implies the vector alpha can be evaluated only if UC is a full rank matrix, thereby specifying the condition for controllability. So that means that is the UC is equal to B A B A square B so on a to the power n minus 1b, which is known as the controllability matrix. Must be a full rank matrix that is an invertible matrix for a system to be controlled. Is that okay? सही है? तो आपका ये जो मैट्रिक्स बी ए बी ए स्क्वायर बी आपका ए टू द पावर n माइनस 1 बी है, ये एक फुल रैंक मैट्रिक्स होना चाहिए, तभी आपका सिस्टम कंट्रोलेबल है. बिकॉज यू सी हियर दैट दिस अल्फा, ये जो अल्फा नॉट, अल्फा 1, अल्फा 2, अल्फा n माइनस 1 है, दिस इज एक्चुअली इक्वल टू दिस, and this is related to u. And controllability is basically a property that is basically defined on the basis of whether ut exists for any random initial condition in the state space, which can take it to the origin. So now we have seen that the condition for that existence of ut is that this matrix, because this can be evaluated on this alpha naught, alpha 1 can be evaluated only if this ut exists. And the condition for this existence of this alpha naught, alpha 1, alpha 2 is that uc must be a full rank matrix or invertible matrix. That gives me the condition for controllability. Is that okay? So we have proven the sufficiency of the theorem. That means the system controllable होने के लिए आपका जो controllability matrix है, जिसको हमने as UC define किया है, ये एक full rank matrix होना चाहिए. Now we will prove the sufficiency. तो हमने prove की. We will also prove, because we'll also have to prove whether this is a necessary condition also or not. So we will prove the necessity. तो वो लास्ट टाइम की तरह ही इंप्रूव करेंगे. So necessary condition, necessity will be, will assume that the system is controllable but the controllability matrix is not a full rank matrix. By contradiction, we'll prove that this cannot be, this is not possible. That a system is controllable and controllability matrix the controllability matrix has to be a full rank matrix for a system to be controllable. So in order to prove the necessity of this theorem, we are assuming that the system is controllable, but the controllability matrix is not a full rank matrix. How is controllability matrix defined as? We define controllability matrix as UC is equal to B, AB, A square B, so on, up to A to the power n minus 1B. We are assuming that this is not a full rank matrix. What does that imply? Rule number 7. Rule number 7.
Yes, sir.
What does that imply, that this matrix is not a full rank matrix?
Sir, that means a determinant is equal to 0.
That's okay. What else?
What else?
सर रूट्स इक्वल होंगे.
जी फिर से बताओ.
Sir, inverse can't be found.
वो तो सेम, वो तो एक ही बात हुई ना.
Sir, unique solution will have a unique solution.
सर लीनियरली डिपेंडेंट होंगे.
हाँ, लीनियरली डिपेंडेंट. इसके जो कॉलम्स हैं वो लीनियरली डिपेंडेंट होंगे. ऑल दीज थिंग्स आर इम्प्लाइड व्हाटएवर यू हैव टोल्ड, बट द पॉइंट दैट आई वाज ट्राइंग टू मेक इज दैट इसके जो कॉलम्स हैं वो लीनियरली डिपेंडेंट होंगे, है ना. तो अगर इसके कॉलम्स लीनियरली डिपेंडेंट होंगे, उसका मतलब क्या हुआ? उसका मतलब ये, दैट मींस दैट इज the columns of UC are linearly dependent, isn't it? That actually means that if you take the linear combination of its columns and put it equal to 0, you will get a non-zero solution for the constants. That means, which implies actually that if I take the linear combination of its columns, that is, if I take alpha naught B plus alpha 1 AB plus alpha 2 A square B plus so on, alpha n minus 1 A to the power n minus 1 B equal to 0. If I put like this, this equation will have a non-zero solution for alpha vector. While alpha vector is what? Where alpha is equal to alpha 1, alpha 2, so on up to alpha n minus 1. सही है ना? Is that okay?
Yes, sir.
Okay. तो इसके लिए इसका एक कोई भी at least one non-zero solution will exist. Then only we can, because we already assumed that these columns of UC are linearly dependent. That means it's not a full rank matrix. So this can be written in short as, I can write it as, or I can write as alpha k as a summation of k is equal to 0 to n minus 1 alpha k, sorry, a to the power kb equal to 0. ये वाली इक्वेशन को मैं ऐसे भी लिख सकता हूं ना? Isn't it? So this will have a non-zero solution for alpha vector. There will be some non-zero solution. Now keep it at the back of your mind. Just keep it aside. Let's call this as equation 1. Now, take this. You know that e to the power at, that is the state transition matrix. As we have just now told that we can, using Kelly-Hamilton theorem, we can express it as a sum of polynomials. So it will be like this. It's represented as a polynomial matrix, so we can write it as beta naught I plus beta 1a plus beta 2a square plus so on, beta n minus 1 a to the power n minus 1. Isn't it? And if I write like this, e to the power atb, I can write it like this, beta naught I plus beta 1a plus beta 2a square plus so on, beta n minus 1 a to the power n minus 1 into b. लिख सकते हैं ना ऐसे? Or I can write e to the power atb equal to summation of k is equal to 0 to n minus 1. सही है? K is equal to 0 to n minus 1 beta k a to the power k into b, because every term is to be multiplied by b. Is that okay? Is that okay?
Yes, sir.
Okay. Now, if I do something like this, if I pre-multiply both sides by alpha transpose, alpha wala vector. So this is alpha transpose e to the power atb is equal to, I can write it like this. So this is alpha transpose summation of k is equal to 0 to n minus 1 beta k ak into b. Now alpha vector also has got k components. So I can write, because this alpha will get accommodated in each one of them, so I'll get it like this. I can write it like this. K is equal to 0 to n minus 1. This will be alpha k, beta k, a to the power kb. Because alpha also has got k components and it is being multiplied to this. So you will have this alpha entering each term of this. So we can write this as summation of k is equal to 0 to n minus 1. Now you know this alpha k and beta k are scalars, so their order can be changed. I can write it like this, beta k, alpha k, a to the power k b. Now summation of k is equal to 0 to n minus 1, a to the power alpha k, a to the power kb is equal to 0 for non-zero alpha. Summation of k is equal to 0 to n minus 1, alpha k, a to the power k, b is equal to 0. So this whole becomes equal to 0 for, because already we have taken this alpha vector is a non-zero vector. So for non-zero alpha. So what do I get from here is that alpha transpose e to the power a t b is equal to 0 for non-zero alpha. इसका मतलब ये हुआ कि ये वाला जो मैट्रिक्स है e to the power atb. Just remember last time what we had done when we were discussing the controllability grammar. Controllability grammar हमने कैसे define किया था? Remember how was controllability grammar defined? Anybody? How did we define the controllability grammar? इसका एक्चुअली implication जो है वो ये है कि क्योंकि इसके ये जो e to the power atb है, अभी जैसे स्टार्ट में किसी ने कहा था कि लास्ट टाइम वी वर डिस्कसिंग द लीनियर डिपेंडेंस इंडिपेंडेंस ऑफ वेक्टर फंक्शंस. So this is basically a vector function. So this vector function has got linearly dependent rows or columns as the case may be, because it's coming out to be 0 for non-zero alpha, isn't it? So this actually implies the vector function e to the power atb has linearly dependent rows, which actually implies that the controllability grammar is a singular matrix, and which actually implies that the system is, because for a system to be controllable, the controllability grammar must be a non-singular matrix. Now what we are getting here is that the controllability grammar is a singular matrix. So that actually implies that the system is not controllable, which contradicts our assumption. Assumption क्या थी हमारी? Assumption ये थी कि सिस्टम तो कंट्रोलेबल है लेकिन कंट्रोलेबिलिटी मैट्रिक्स फुल रैंक नहीं है, तो वो assumption ही कॉन्ट्रडिक्ट हो जाती है. So that actually which contradicts our assumption and hence proving the necessity of this condition. Is that okay? जब तक पुराने लेक्चर्स नहीं पढ़ोगे तब तक नया लेक्चर समझ नहीं आएगा. आप कंट्रोलेबिलिटी पे जितना टाइम हमने दिया है इतने टाइम में 10 टॉपिक मेरे कंप्लीट हो गए होते हैं. बट अनलेस यू टेक इंटरेस्ट दिस इज ऑल गोइंग वेस्ट. Could you get this thing? What I was trying to say here? What I have got here is that alpha transpose e to the power atb is equal to 0 for non-zero alpha. So this is actually this alpha transpose e to the power atb. It is actually a linear combination of its rows or columns, whatever the case may be. So what I am trying, if it is equal to 0 for non-zero alpha, that actually means that it has got linearly independent rows. So if it has got linearly independent rows, that means it is a singular matrix, or it's not a full rank matrix, whatever you want to. ये जो controllability grammar है वो singular matrix है, and as you know that the system for a system to be controllable, the controllability grammar must be a non-singular matrix. Now, since it's coming out to be a singular matrix, the system is not controllable, which contradicts our assumption and hence proving the necessity of this condition. The necessity condition is that The necessary condition is that for a system to be controllable, the necessary condition is that the controllability matrix must be a full rank matrix. Is that okay? Yes.
Yes.
आप लोग मैथमेटिक्स देखोगे, थोड़ा बहुत पुराना लेक्चर भी देखोगे, उसमें देखोगे कंट्रोलेबिलिटी ग्रामर हमने डिफाइन कैसे किया था और कंट्रोलेबिलिटी ग्रामर की बेसिस पे हमने कैसे बताया था, फिर वो जो पूरा जो फर्स्ट पार्ट था थ्योरम का वो भी देखोगे एक बार, and then you'll be able to understand it. Otherwise it's simple mathematics, it's not that very complicated mathematics. Is that clear?
Yes sir.
तो ये वाला कंडीशन जो है कंट्रोलेबिलिटी देखने का, ये वाला टेस्ट जो है कंट्रोलेबिलिटी देखने का, ये सबसे पॉपुलर टेस्ट है और सबसे इजी टेस्ट है कंट्रोलेबिलिटी को देखने का कि आपका जो कंट्रोलेबिलिटी मैट्रिक्स है वो फुल रैंक मैट्रिक्स होना चाहिए। मींस अगर आपको एक स्टेट स्पेस मॉडल दिया गया है और आपसे पूछा जा रहा है कि बताओ ये सिस्टम कंट्रोलेबल है कि नहीं है, तो आप क्या करोगे, आप कंट्रोलेबिलिटी मैट्रिक्स बनाओगे। कंट्रोलेबिलिटी मैट्रिक्स कैसे डिफाइन किया हमने? इट्स द मैट्रिक्स डिफाइंड एज b a b a square b up to a to the power n minus 1b। और मैट्रिक्स जब बनेगा उसके बाद आप उसकी रैंक देखोगे। If it is a full rank matrix, then you can straight away conclude that the system is controllable. And if it is not a full rank matrix, the conclusion will be that the system is not controllable. Simple yes no में आंसर मिलेगा कि सिस्टम कंट्रोलेबल है कि नहीं। Is that clear?
Yes sir.
मान लीजिए आपको एक स्टेट स्पेस मॉडल, एक रैंडम स्टेट स्पेस मॉडल अगर हम ले लेते हैं, let's say you have got x dot equal to something like 0 1 0 0 0 1 minus 6 minus 11 minus 6 x plus 0 0 1 u। ये आपको एक स्टेट स्पेस मॉडल दिया गया है और आपको पूछा जा रहा है बताओ कि सिस्टम कंट्रोलेबल है कि नहीं है। तो कैसे करेंगे? We'll define the controllability matrix, that is UC, that will be AB, it is up to a to the power n minus 1b। इसमें n क्या है? 3। तो इसमें तीसरा वाला कॉलम लास्ट वाला कॉलम होगा, that is a square b, isn't it? b तो पता ही है आपको, b is equal to 0 0 1, तो पहला कॉलम तो इसका दिया हुआ ही है। then AB, isn't it? AB means 0 1 0 0 0 1 minus 6 minus 11 minus 6, and it's to be multiplied by 0 0 1. So what will I get it as? Yes.
So 0 1 minus 6.
1 minus 6. So this is the last column of this, है ना? ये तो हो गया AB। और a square b क्या आएगा फिर? a square b के लिए you will have a into ab, means ये जो यहाँ पे ab आया, you don't need to do a square b will be actually a into ab, isn't it? So your a0 what is it, 0 1 0 0 0 1 minus 6 minus 11 minus 6, then multiplied by AB is 0 1 minus 6। ठीक है ना? सही है? So what will we get this as? This will be 1, then minus 6, and then minus 11 plus 36, that's 25। Is that okay? ठीक है ना?
Yes sir.
So what will UC now? UC will be 0 0 1 0 1 minus 6 and 1 minus 6 25। अब आपको देखना है कि ये फुल रैंक मैट्रिक्स है कि नहीं है। उसके लिए आप इसका डिटरमिनेंट इवैल्यूएट कर सकते हो। ये लोअर ट्रायंगुलर मैट्रिक्स है, नॉन जीरो एंट्रीज हैं डायगोनल पे, so this matrix is going to be a full rank matrix, isn't it? मैट्रिसेस स्टार्ट में मैंने कहा था कि मैट्रिसेस आपको रिवाइज करनी पड़ेंगी अच्छे से। इसका डिटरमिनेंट क्या आएगा इस मैट्रिक्स का?
1 sir.
क्या आएगा?
-1.
-1।
Yes sir.
Okay. So whatever. So that means determinant of UC is not equal to 0. which implies UC is a full rank matrix, which actually implies that the given system is controllable. Is that okay? So a complex mathematical or a complex physical problem of judging the controllability of a system has been reduced to a simple mathematical problem of determining the rank of a matrix. And by evaluating the rank of this matrix, controllability matrix, you can actually tell whether the given system is controllable. Is that okay? And as I told you that this is one of the most frequent and most popular tests used for obtaining the controllability of a system. इससे पहले भी मैंने आपको एक टेस्ट दिखाया सिस्टम की कंट्रोलेबिलिटी ऑब्टेन करने का. एक तो हमने देखा डायगोनलाइजेशन करके. डायगोनलाइजेशन में बी के एंट्रीज देख के आप बता सकते हो कि सिस्टम कंट्रोलेबल है कि नहीं है. लेकिन उसके लिए जो मैथमेटिकल कॉम्प्लेक्सिटी उसमें है, डायगोनलाइजेशन में जो मैथमेटिकल कॉम्प्लेक्सिटी है, दैट्स टू मच. It means for diagonalizing you have to actually obtain, you have to actually do the similarity transformation. Similarity transformation के लिए आपको इनवर्स निकालना पड़ेगा, तो वो थोड़ा सा कॉम्प्लिकेटेड है. दूसरा टेस्ट जो मैंने आपको दिखाया, दैट इज अबाउट कंट्रोलेबिलिटी ग्रामीन. कंट्रोलेबिलिटी ग्रामीन के लिए एक कॉम्प्लिकेटेड मैट्रिक्स का इंटीग्रल ऑब्टेन करना है, which is although it's a very good theoretical result, but practically इसके थ्रू सिस्टम की कंट्रोलेबिलिटी ऑब्टेन करना डिफिकल्ट है मैथमेटिकली. Now this one, by obtaining the rank of a controllability matrix, जिसकी की column simple matrix multiplication से obtain किए जा सकते हैं. So it's one of the easiest and one of the most popular and frequent tests used for judging the controllability of the system. Is that okay up till now? Yes.
Yes, sir.
ठीक. Now let's move a bit further. I'll show you one more test of one more what we call fact about controllability, but in the next class. Today, let me talk about something else, that is properties or an important property of controllability. Property goes like this: controllability of a system is invariant under any similarity transformation. जैसे हमने स्टेबिलिटी प्रूव किया था कि आइगन वैल्यूज जो सिस्टम के होते हैं वो इनवेरिएंट होते हैं अंडर एनी सिमिलैरिटी ट्रांसफॉर्मेशन, बिकॉज़ स्टेबिलिटी इज अ सिस्टम प्रॉपर्टी. Similarly, controllability is also a system property. So if you have a given state space model and if it is controllable and you do some similarity transformation and obtain an equivalent state space model for the system, the property of controllability will remain preserved. That means the state space model which has been obtained after similarity transformation will also be controllable, because controllability basically is a system property. It doesn't depend upon the representation of the system. It doesn't depend upon using which state variable models you have actually represented the system. Are you understanding this? For example, you have got x dot equal to x plus bu. So whether it is controllable or not controllable, that property will be preserved when you do the similarity transformation. For example, if I do some similarity transformation here, how do you define a similarity transformation? Yes.
Sir, x equal to pz where p is invertible.
P is invertible matrix. I define something like x is equal to pz. Yeah. P is an invertible matrix. X is equal to pz, z is equal to px. किसी भी तरीके से define कर सकते हैं. That's one and the same thing. So what will I get this as? I'll get the model as z dot equal to a dash z plus b dash u. Is that okay? Where A dash is equal to P inverse of AP and B dash is equal to P inverse of B. ठीक है ना? अब जो पहला वाला स्टेट स्पेस मॉडल है दिस वन, इसका जो कंट्रोलेबिलिटी मैट्रिक्स होगा, कंट्रोलेबिलिटी मैट्रिक्स, let me call that as UX. Will that be equal to B, AB, A square B, so on up to A to the power n minus 1. Okay. So assume that system given by equation 1 is controllable. What does that mean? Which implies UX is an invertible matrix. Isn't it? Now it will be the controllability matrix for this transformed system. इसका controllability matrix क्या होगा? Let me call that as UZ. That will be B dash, A dash B, A dash square B, so on, A dash into n minus 1B. सही है? So what we are stating is that if this model is controllable, तब ये जो transformed model है ये भी controllable होगा. That means that it's invariant. So how do I prove this? So I can write this as UZ is equal to, instead of B dash I can write P inverse B, isn't it? Instead of this A dash B I can write P inverse AP and P inverse B. Are you getting me?
Yes, sir.
अब आपका ये A dash square है. A dash square हम कैसे लिख सकते हैं? A dash square we can write as A dash into A dash, isn't it? A dash square can be written as A dash into A dash. Now A dash I can write as P inverse of AP and A dash this also I can write as P inverse of AP. So A dash square की जगह मैं लिख सकता हूँ P inverse of AP दो बार. P inverse of AP, then B will be P inverse of B and so on like this. Is that okay? Now P is an invertible matrix. So P into P inverse it's equal to I. This P into P inverse this will be I. This P into P inverse this will be I, because P is an invertible matrix as per the definition of similarity transformation. So what will I get UZ as? This is first as P inverse B. Then this will be P inverse AB. Then this will be, this is I, this will be P inverse A square B. And similarly, other terms also you will get P inverse A to the power n minus 1B. A to the power n minus 1B. Is that okay? So P inverse I can take out. What will I get inside? That is B, AB, A square B, so on, up to A to the power n minus 1B. Or I can write it as P inverse. And what is this? This is your UX. Is that clear? So this UZ is coming out to be equal to P inverse into UX. UX भी full rank matrix है, क्योंकि मैंने वो already assumption ली है कि original system controllable है. System given by equation 1 is controllable. This is also an invertible matrix. The product of two full rank matrices is also a full rank matrix, and the rank will be equal to the rank of these matrices. You know what is the rank of this P? इसका rank क्या है? The rank of this is n. और इसकी rank क्या है? इसकी rank भी n. The product of two matrices each having rank n will be a matrix of rank n, implying that UZ is a full rank matrix. Which actually implies that the system given by equation 2, कहाँ गया वो system जो हमने स्टेट स्पेस मॉडल डिफाइन किया था, ये वाला, which implies that the system given by equation 2 is also controllable. Is that okay? Which goes on to prove that the controllability property means if the original system is controllable, the transformed system will also be controllable. What if the original system is not controllable? That means this UX will have rank less than n. Isn't it? Yes.
Sir.
Yes, sir.
UX will have rank less than n. तो जब दो मैट्रिसेस को हम प्रोडक्ट लेंगे जिसमें एक की रैंक n है दूसरे की रैंक लेस देन n है, तो प्रोडक्ट मैट्रिक्स की रैंक लोएस्ट ऑफ द टू रैंक्स के बराबर होगी, मींस उसकी रैंक भी उतनी वही होगी जो ux की होगी, implying that the system given by equation 2 will also be not controllable. That means the property of controllable is preserved when you do a similarity transformation. If the original model is controllable, the transformed system will also be controllable. If it is not controllable, the transformed system will also not be controllable. Is that clear?
Yes, sir.
So that's it. I'll stop here. You'll tell me the doubts about it in the Friday's class, and we'll also be discussing something more about controllability. And I'll now move you towards the design of controllers based upon this property of controllability. How do we design a controller? If we say that the system is controllable, then how actually do we design a controller based on that? Is that clear?
Yes, sir.
I'll be stopping here. You can just leave and go for the next class. Thank you.